In this video, we're going to look at ratios and proportions and some of the fundamental properties of proportions. So before we get into that, let's go through a quick review of what a ratio and proportion actually is, as these two terms are often confused. A ratio is just a relationship of relative size between two numbers, and that's defined by their fractions. So for example, if I have the ratio of 2 to 3, what that really just means is the fraction 2/3. Now, many times we'll have ratios which can be reduced, like the ratio 5 to 15, because that represents the fraction 5/15, and there's a common factor of 5, I can reduce that fraction to 1/3, and the ratio 5/15 is the same as the ratio 1/3. For that reason, the ratio 5 to 15 is proportional to the ratio 1 to 3 because that is the equivalence of two different ratios. Typically, we will represent a ratio in its simplest form, which is the form in which no more common factors exist. So for example, if I have the ratio 6 to 12, because there is a common factor of 6, I can reduce that ratio to its proportional size 1 to 2. So the ratio 6 to 12 is proportional to the ratio 1 to 2. Okay? So now let's look at an actual example of how to use this information. In the triangle over here, triangle ABC, I want to find some specific ratios within that triangle. So the ratio AC to BC will be proportional to the length of side AC, which is 12, to the length of side BC, which is 18. And because there's a common factor of 6 between those two numbers, I can reduce this ratio to its proportional size 2/3. And again, we will always represent ratios in their simplest form. If I look again at the ratio of BC, which is 18, to AB, which is 48, I get the ratio 18 to 48. And because there is again a common factor of 6, I can further reduce this ratio to its proportional size 3 to 8, or 3/8. Now, what we have in part C is what's called an extended ratio. An extended ratio is useful for letting us know the relative size of more than two things. And it works in very much the same way that a normal ratio does. This ratio will be proportional to the length of side AC, which is 12, to the length of side BC, which is 18, to the length of side AB, which is 48. And again, because all three of these numbers share a common factor of 6, I can reduce this ratio to a proportional size of 2 to 3 to 8. Okay. Now, ratios and proportions are useful in a lot of other ways as well. Say three numbers aren't known, but I do know their ratio, 1 to 4 to 5. Which of the following is not a ratio which is proportional to the ratio 1 to 4 to 5? So I'm trying to find which of these is proportional or equivalent to 1 to 4 to 5 and identify the one that is not. So the first one I'm actually going to point out that definitely is proportional is 1 to 4 to 5. This ratio is not the one I'm looking for because it's actually equivalent to the one here. You can even see it. Any ratio is proportional to itself. So my task is to look at the remaining three and find which one is not proportional. Well, to do that, let's just reduce each of these ratios to their simplest form to compare them. So 5 to 20 to 5 shares a common factor of 5 between each of those numbers. 5 goes into 5 once, 5 goes into 20 4 times, and into 25 5 times. So this is definitely proportional to our given ratio, so that's also not the one I'm looking for. 4, 12, and 18 all share a common factor of 2. 2 goes into 4 twice, into 12 6 times, and into 18 9 times. and I look again and I see that 2 and 6 share a common factor of 2, but that common factor is not a part of 9, so I won't be able to further reduce this ratio. And since 2 to 6 to 9 is not proportional or not equal to 1 to 4 to 5, this will be the answer I'm looking for. So then, is that the only one? Well, let's look at part C. Now, part C, just like part A, or question A, has a common factor in it. The common factor in A was 5, and I was able to reduce all three numbers by a factor of 5. The common factor in C is x, so I can divide each term by x. And x goes into itself once, into 4x 4 times, and into 5x 5 times. So I can see that this ratio is actually proportional to 1 to 4 to 5. So the only one which was not was choice B. This idea that I can introduce any factor into a ratio to get a proportional length is fundamental in how we're going to be using ratios and proportions. Looking at question 3, it says the angles of triangle ABC are in a ratio of 3 to 4 to 5. Find the measure of each of the angles of this triangle. Well, the question is, can these angles actually be just the numbers 3, 4, and 5? And unfortunately not. And I'm relying on a fundamental idea which we've studied earlier in the year, that the measures of the three angles of a triangle must add up to 180 degrees. And because 3 plus 4 plus 5 only add up to 12, it's clear that the angles are not 3 degrees, 4 degrees, and 5 degrees. So there must be some other ratio which 3 to 4 to 5 is proportional to. So I'm going to introduce some variable called x, and I'm going to let x be that common factor that's missing between the three measures of this angle. So we've seen in the previous question that this ratio is always proportional to another ratio with any common factor in it. I'm just letting x be that common factor. Therefore, 3x plus 4x plus 5x has to be 180 degrees. So I get 12x equals 180, and when I divide both sides by 12, I'll end up with the value of x is 15. Well, now that I know the value of x, I know the actual ratio that these original three angles must have been in. 3 times x would be 45, 4 times x would be 60, and 5 times x, which again is 15, would be 75. So since these three are in the same ratio or are proportional to my given ratio, and they add up to 180, they meet both of the conditions of the angles in triangle ABC. Thus, those three things must be the answer I'm looking for. Those are the three angles of triangle ABC. Okay. Now, when we're working with ratios and proportions, it's sometimes helpful to represent them in similar ways. And for that, we're going to use proportions. Now, proportions have several properties which help us manipulate them into more conveniently representing them. So first, before we go into the properties of proportions, let's talk about what actually makes up a proportion. So again, a proportion is just the equivalence of two ratios. So here I have two ratios, the ratio of A to B and the ratio of C to D. Now, when we start describing these properties, we're going to use some terms which refer to different parts of this proportion. So the first part is called the means. Now, the means of a proportion are just the two middle numbers. When you write a proportion out, it's the two numbers which occur between the other two values, which are the extremes. So the means, just like the mean of a set of numbers is the average, occur in the middle. Averages occur in the middle, and the extremes on the outskirts, on the outsides of that proportion. Now you can also represent this as a fraction. The extremes, again, will occur on either end of the proportion, and the means will occur in the middle, or in between those two values. And to help or the way that I help to remember it, is that if you think about when you read a book, you read from top left to bottom right. So the extremes or the outsides of a page that you would be reading, the first part and the last part would occur in the top left and the bottom right of that page, and then everything in the middle, or its means, occurs in between. So that's one way that I help to remember what the parts of a proportion or where they will show up. So now that we've just talked about the parts, there are several ways that we can represent this proportion. So given this proportion, A over B is equal to C over D, we could represent it in any of these 5 equivalent ways. So the first is probably one that you've definitely seen before, and it's basically I can multiply the means and the extremes together and they will be equal. You've probably seen this and heard it explained as cross-multiplying. Now all cross-multiplying is a special application of what's called the product of the means is equal to the product of the extremes, which we abbreviate by POM equals PO. Another example of an equivalent proportion would be using what's called the means property. And it's equivalent to exchange the mean values of a proportion. If this proportion is true, then this proportion will also be true. And there's a quick and easy way to justify that. So this is the how this proportion works, or the why it works. So if I start with the proportion A over B is equal to C over D, if I'm given this, then the very first thing I could do is use the property we just discussed, the product So I'm going to go ahead and prove to you that if this proportion is true, then this proportion must also be true. And I'm going to do that in a standard 2-column format using statements and reasons. So first, I'm going to take my given proportion, which says that A over B is equal to C over D. And I'm going to use the only property that we've discussed so far, this cross-multiplying property, or as we'll formally call it, the product of the means is equal to the product of the extremes. So now I know that AD is equivalent to BC. Okay. Well, now it's just an equation, and what I can do is divide both sides by a particular number using the division property of equality. Remember that from way back when we were doing proofs. And the number I'm going to divide both sides by is a specific one that I want to use, which is B, is a specific one which I want to use, which is the value C times D. Now, when I divide C times D into this equation, watch what happens. And I'm going to do it over here in some scrap space. AD equals BC. If I divide both sides by CD, on this side, the D's will cancel out, and on this side, the C's will cancel out, and I'm left with A over C is equal to B over D. Just doing some simple division. So notice that I got from my given proportion and I arrived at a new proportion. It's a new sequence of numbers. It's different from the proportion I had before. And what looks like the overall effect is that I've just interchanged the two mean values. Now, I'm going to go through the remainder of these properties and they can all be justified in a similar way to what I've just done, but we'll see why they're useful in just a moment. So the remaining properties are the extremes property, which is just like the means property, except you can interchange the extremes values. The reciprocal property, which is from this original proportion, I can take the reciprocal of both sides and it would still be proportional. And the last one that we're going to talk about in this video is the addition property of proportions, which I can add on the denominator value to each side and it will still be in proportion. Now the last one is actually quickly justified by just thinking about the addition property of equations. if you look at these values, and I think about what happens, I could technically think of, again, this is the y as to this, why this is equivalent. This is really just A over B plus B over B is equal to C over D plus D over D. Well, B over B is just 1. And D over D is just 1. So really all I did was add 1 to both sides of this original proportion, which is why it's the same. It's called the addition property of proportions, but it's basically the same thing as the addition property of equality. Okay, so those are the five main properties that we're going to be concerned with. So what we're going to do is look at a couple of examples of how you can see them and apply them. So you should have this on your sheet. What I'd like you to do is to go through each of these 1 through 5 and tell me what this value is going to be proportional to and what property of proportions would justify your conclusion. Now, after you've done that, you can go ahead and look at the true-false questions underneath and take your best educated guess as to what you think about those. Then we're going to go over them together in this video. So you have an idea of what I'm asking you to do. In the first one, I'm going to look at it and I notice that y over x is really just the reciprocal of x over y. So if I was to use the reciprocal property of proportions on this proportion, y over x would just be equal to the reciprocal of 5 over 2, which is 2/5, and that's using the reciprocal property. So when you pause this video, go ahead and answer the rest of these questions, and then we'll go over them when you come back. Okay, so in question 2, I have m over 5 is proportional to n over 6. So the ratio of m to 5 is proportional to the ratio of n to 6. So now I have over here 5n, which is the product of the means. Well, the product of the means would be equal to the product of the extremes. So I expect this to be 6m by the POM equals PO property. In the third one, I have a over 12, and I'm trying to figure out what that ratio is proportional to. Well, I was given that 4 to a is proportional to b to 12, so it looks like I just exchanged the a and the b, and I'll have my a over 12. So I'm going to use the means property to do so, and I end up with 4 over b after I've interchanged those two values. In 4, I have the ratio of a to 3 is proportional to b to 4, so that a to b must be proportional to 3/4 by the means property again. I've just interchanged the b and the 3. Now you could also have thought of it as using the extremes property and then the reciprocal property, and you'd end up with the same ratios. There's a number of different ways of reasoning it through. And in the last one, if I look at it, again I have a sum value, and I'm reducing this down to x over 5 by basically just subtracting 1 from both sides. And I can use the addition property of proportions to do that. Okay. Now, looking at the true-false questions, x is to y as 3 is to 4, then x must be 3 and y must be 4. That's actually false, and it's one of the most common ones that students get wrong. To illustrate why, think of it this way. What this is just saying is that the ratio of x to y is proportional to 3 to 4. But another ratio that it would be proportional to would be 6 to 8, or 9 to 12, or 15 to 20. In fact, there's an infinite number of ratios which are proportional to 3 to 4. So x and y could be any of these values. Because I don't know what their actual number value is, I only know what their relative size is to each other. That's what a ratio tells me. I can't conclude that the two values must be equal to these numbers. Okay. Now, in the other two, I have these. if and only if, meaning it's equivalent to say that 3x equals 10 as it is to say this proportion. That's actually true using the product of the means equals the product of the extremes. 3 times x would be the product of the extremes, and 5 times 2 is the product of the means. And in the last one, if I look at this, 2/5 is just the reciprocal of 5/2. So the reciprocal of 1 over x is actually x over 1, which reduces to just x. So this is true by the reciprocal property. So we'll see how we can use these properties in further examples as we continue in this material, and we'll see how we can use it in proofs when we start talking about similar polygons.